Sorry for the delay. Oops. Yeah, so I lost my paper. I was carrying it while entering the building, but then, yeah. So today it's very nice lecture. So um, let's start with it. So first, we already discussed with you what happens if after we prove our problem is NP complete. And so then we know there is, we can go to our boss and give him some warning that there is no ideal scenario, that you're provably fast for all instances and compute exact algorithm. But then you can be very happy because, so let us say, what means P? So we go back to production problems like previous lecture. Problem isn't P. It means that algorithm that gives exact answers in polynomial time, always in polynomial time, worst case. Yeah, for all instances works in polynomial time. All instances polynomial time. So three things: exact answer, uh, polynomial time on all instances. And so the next thing is drop one of the three. So it's almost always, I don't know any case where you cannot have any two out of three. So you tell him which one you want to drop. So maybe a special case, it means that, okay, we will limit our graph. We will make an extra assumption on the input. For example, if input is a tree and you need to solve vertex cover, you can do it by some greedy algorithm. If he says, okay, no, I don't know any good way to create special cases, maybe approximate answer is enough. It is topic of previous lecture. And now we look to the case where we are happy not to run in polynomial time. So topic of today is optimize exponential searches. Yes, and it's very pleasant topic because we will speak about what kernel. It's about strategies to reduce the size of the problem before we run brute force search. Because if we go to half the size of our problem, then it's enormous if the size appears an exponent. Okay. And so one of the cool things we'll do is consider vertex problem and say that if the graph, if we want to find vertex cover of size like 200 or even 400, then we can do it if we can pay for a few CPU years. Or even vertex cover of size, like in the programming exercise for programming engineering, there is second part in February where we will have more lectures about parameterized complexity. And there in the programming, I will ask you to generate some vertex. So give you graph pretty adversely generated, and you need to find vertex cover of size 80, and people can do it in 1 second in Python. Okay, so we are back now. Is the streaming still happening? Okay. Yes, streaming is happening. Okay, we're back now. Yes. Total delay of 10 minutes. So, by the way, is it readable? Can you read the board? Can somebody write in chat whether they can see the board? Or let me put it on gallery. Yeah, it looks pretty good on my PC. Okay. So where were we? Yeah. So I just said that vertex cover problem, like if you can pay for a few CPU years, so if problem is really important to be optimized, like you need to compute one time a solution in the product, and then each node less in the vertex cover is like percentage less cost of the product. So then maybe you want to pay 10,000 dollars or euros for optimization. So yeah, so then we optimize search. Okay, so let us consider vertex cover problem for the start. So it's a very popular problem to illustrate things on the so imagine we do brute force search, or no, let's do a click problem. So imagine we do brute force search. So what we do, we have a graph and a number k. We want to know whether there is a clique of size k. So then brute force is trying all sets of size at most k. And this will take time. Hello. So this will take time and choose k. And this is roughly equal to n to the power k. So this is, you're lucky because there were so many technical issues. We only started now. So yeah, if we brute force click problem, finding click of size at most k, it's time n to the power k.
Time space squared equals just check.
Yeah.
Essentially.
But maybe our graph has some special property that the degree is not too big. And so then there is an algorithm that runs inside in time 2 to the power d, if d is maximal degree, times poly n. So which is much better if d is not too big. So if you're like you want to know, like Facebook, is there a clique of size 300 people or whatever network people use? Are there 300 people that are friends of each other and the maximum degree is 300? There used to be like a limit on Facebook in the beginning. Yeah, because people were very concerned about privacy. And so most people only had like 20 or 50 friends. They only put people they know. And not everyone has Facebook. So it's, I mean, so yeah, but okay. And now I'm old, so I use people say, "Oh no, this is for retired people." Yeah. Okay. So yeah. So, but back to our algorithm. So 2 to the power d is much better than n to the power k. 1 billion to the power 300 is much better than 2 to the power 300. So what is this algorithm? So can you guess it? So
we take a vertex and then we choose all the subsets of size k of this d.
Yeah, exactly. Neighbors. And so for every node, we check whether there is a clique that contains this node. And the clique can only consist of neighbors of this node. And so we iterate over each node and then look at all the subsets of this node. So note that there can be no clique of size bigger than d plus 1. Because every node has at most d neighbors, and in the clique, every node is connected to all the other nodes in the clique. Okay, so another example is a vertex cover problem. So now in the input is a graph and number k. Question, is there a vertex cover of size at most k? So also there is algorithm. So brute force and choose k way too slow. And again, there is algorithm, so of size 2 to the power k. So if we need to find a vertex cover that's not too big, we can do it efficiently. And so was the idea. Ideas to understand, well, maybe you can guess it, because it's similar as approximation problem. So the idea is the same. So we pick an edge. Okay, I will tell it. So we pick an edge, and then we know that one of the endpoints, at least one of the endpoints of this edge must be in the vertex cover. So we will make a branching program. We pick one node and we say either this node is in the vertex cover or it's not in the vertex cover. But then if it's not in the so if this node is in the vertex cover, we can recursively solve the problem for one node less. But if it's not in the vertex cover, then we know the other node must be in the vertex cover. And we can also recursively solve for one less. And so we will have a tree, a branching tree. This will be important. I don't know if it's visible, this marker. Yes, it seems to be visible. And so each time we have two options. And actually, if there is a node of large degree, we can do better. So if we pick a node of large degree, then we say either this node is in the vertex cover or all its neighbors is in the vertex cover. And so we have a binary tree. And on one side, we start with graph GK. And here we start with some reduced graph and k minus 1. And here we start with reduced graph and k minus the degree of this node. And so we just need to pick it. So clever idea is pick the node with largest degree, like the heuristic algorithm on the optimization problem. Okay, so these are examples. So let us now say what is the class FPT.
So we can find if this runs to power of k on the right branch, we don't use k.
Yeah, so in the
one.
Yeah.
So the tap of the tree is
Yeah, the
tree is fine.
Yeah, thank you. Yeah, I should say it completely. So please, everyone should react. So the depth of the tree is at most k, and we have a binary tree. Okay. So so now let us say what is definition of class FPT. Or let's do one more example before going to the definition. So the next example is cluster graph problem. So what is cluster graph? It is a graph that's a disjoint union of clusters. And the question is, can we remove k nodes so that the remaining graph is a cluster graph? So that is okay. Yeah, you can define it with edges as there's also a common variant. So cluster graph problem. So it's from biology. So people get some DNA and fragments of DNA, and they check whether it's somehow consistent or not. They want to know how many pieces of DNA, or how many different species they have in their sample. And then they have some bad readings, and they want to remove the bad DNA point. So they want to minimize the number of bad readings. And then now, so an example of a cluster graph is this graph, or this graph, and isolated nodes. So here are two examples of cluster graphs. Still cluster graph, just a single click as well. Okay, and so what is algorithm to find so the input is a graph, a question, and so then there is some parameter. So in parameterized complexity, every problem also has a parameter. which is k, an integer. And we will, for now, assume parameter as part of the input. And then the question, can remove k nodes to obtain a cluster graph. So, and there is algorithm that solves this problem in time 3 to the power k poly n. Is it readable? Difficult, I guess. Okay, we should use the blue marker. Yes, and so how does it work? So the observation is that in a cluster graph, any two edges that share one endpoint. And so if we look to any path of length 2, the endpoint should also be connected. So property in cluster graph, every subgraph of the form this. So for every subgraph, so for every 3 nodes, we cannot have this, but we can have 3 isolated nodes and one node and another node and a triangle. So plus permutation, so up to permutations. And so here we have 3 variants. So this is not okay, and these and these and these are okay. So how do we prove that? If our graph is a cluster graph, we have only for every 3 points, we have such a structure. And if our graph is not a cluster graph, we must find such a structure. So how can we prove this? Yeah, that's the dangerous part. If something is clear and obvious, but you cannot say precisely
Okay,
what.
well, suppose there is no such a subgraph in the graph.
Well, let's do the easy direction first. So suppose we see this form,
Okay,
then it's clearly not a cluster
because
graph.
it's not a
Yeah.
cluster.
Okay. So now suppose that this form, so it's not a cluster graph. Let's suppose it's not a cluster graph. So then we must find 2 nodes that are connected by a long path, but not connected. So 2 disconnected nodes, but they are connected by long paths. So that's what you are saying. So yeah, so imagine that we have no cluster graph. So it means that there are 2 nodes and they are not, they are connected. Yeah. But not, let's use a bit more. Like this. Okay, so then let's try to find this forbidden structure. So
Just choose any
yeah.
node, and if choose any node between those two on the
Yeah.
path. So if this node is connected with both of the endpoints, then just remove then this is the structure, and otherwise we can replace an endpoint with the point which we choose.
Yeah, so I would do like follow the 2 first edges. If they are not connected, we are finished.
I mean,
And-
you can
yeah.
find the shortest path and each such nodes would be forbidden.
Yeah, exactly. Yeah, cool. Yeah, that's really short formulation. Yeah, that's so clear. So we take shortest path, and then any 2 nodes on the path must be disconnected by short definition of shortest. Okay. So now we understand what is forbidden pattern. And so what is algorithm that runs in 3 to the power k time up to polynomial? So we will have branching algorithm, and there will be 3 children in each node.
So K, okay.
Okay, so what we will do is we will check all triples of nodes and check whether the forbidden structure appears. If we find no such triples, we have cluster graph. Otherwise, we find such a triple. And now we know that we need to remove at least one of the 3 nodes to make to obtain one of the allowed structures. And so we have 3 branches in our tree. And then we recurse. But now we already, in each branch, we removed exactly 1 node. So we have the same thing. So the parameter. So we start with G and K in the root, and then we have 3 branches. Where, so either we know the answer, or we have 3 branches where we have G1 with K minus 1 and so on. G2, K minus 1 instance, G3, and so on. So each time we remove 1 node and then we recurse. And we know that the depth of the tree again is K, but now the size of the tree is 3 to the power. So number of nodes in the tree is 3 to the power K plus, at most K plus 1, something like this. And in each node, how much work is done? We have to find such a triple of nodes. And so it is n to the power 3. I mean, it can be done even faster, but okay, we don't care about the polynomial at the moment. So that's a cluster graph problem. Okay, so examples we already did. And now let's define the class FPT. And so before we had words, the inputs were words. So a problem was a subset of words. Now we have a word and a parameter. So there are 2 variants. The parameter is part of the input or it's not in part of the input. We will almost always speak about the case where parameter is part of the input. So I will view this as part of input. There was one exception when we speak about tree width, we don't make this assumption. So, but it's not this year, it's for people in February. Okay. So let us write the definition. So parameterized problem is a subset. So parameterized problem is subset of n times sigma star. And so we have alphabet sigma, and we take, let me take a better marker. Now, important moment of n times sigma star. So parameter and words. And the task is to check whether the pair is in the set, yes or no. And then we say that the problem is FPT. So the parameterized problem is fixed parameter tractable. So it's a class of problems. If there exists an algorithm whose runtime is any computable function of the parameter times a polynomial in the length of the instance, where the length of the instance is parameter plus size of word. So parameterized problem is FPT if there exists algorithm and computable function f and constant c, such that for all kx parameterized problem, I need to problem P. sorry, that for all kx. No, I don't need to name for the problem. For all kx in n times sigma star. Algorithm answers correctly in time. Time f of k times length of x plus k to the power c. So this is definition. So this is our most important definition for today. Okay, so let us consider a colorability problem. And so parameter is k, question, and so an example. Well, first, let us say that P is a subset of FPT. Note that P is a problem, and P is a subset of strings. So we have a different parameter here, but let's just insert one or whatever you want for this parameter. And then I claim that P is subset of FPT. And the reason why, well, there exists polynomial time algorithm. So we know that, okay, let's say that K is at least 1, for the special case 0, to exclude this. And then the f of K can be some constant times this. So this is clear, right? So then let us do an example. So input is a graph. The parameter is the colorability problem. So parameter is K. Number of colors. Yeah, number of colors. And the question, can we color it with K colors? Can G be colored? So the vertices be colored with K colors. And so this, if P is not equal to NP, then this problem is not FPT. And so P not equal. So you remember why we proved that tree colorability is NP complete. So if tree colorability can be solved in polynomial time, then we have P equals NP. Implies K color not in FPT. So this is an example. Another example is exponential time hypothesis implies that clique is not FPT. So now I need to say two things. So clique problem with the size as parameter. And so given K, graph and K, find clique of size at most K. This problem is not in FPT. So it's very different from vertex covered problem. Okay, I need to say what is exponential time hypothesis. Next lecture, it will be very important, this hypothesis. So, so this is hypothesis that cannot be solved in sub-exponential time. Okay, this is like the rough statement of the problem, because there are some subtleties. So the precise statement is that there exists some C bigger than 0, such that sat, sorry, I forgot it. It's like K sat. No. Okay, somebody should check Wikipedia. Sat with n variables. I forgot whether it's sat or K sat. Cannot be solved. Or it's not in. It's 3 sat. Oh, yeah. With n variables is not in.
Wait, they're both. Where is it? Oh no, I'm lying.
Yeah, there is. Make sure you don't check strong exponential time hypothesis, because that one is with 3 sat. But I think it's just sat. Well, anyway, on YouTube, I will put the right answer at the bottom. So I think it's just SAT. SAT with n variables is not in time 2 to the power c of n. So there is a subtlety, like a sub-exponential. So it might happen that for every c, there exists an algorithm that is in time 2 to the power cn, but it's a different algorithm for every c. So there is kind of subtle borderline case. Oh, battery is low. So we have no electricity at all. Why it's not charging?
The battery.
Plug. There is a plug. With the electricity in the plug. No, not charging. Okay. I'm really sorry for, but I don't know what to do. And there is no electricity. So is there some other device? And see whether there is a problem with my laptop. Okay. Then for the okay, then I have a few minutes left. So let's continue teaching. Yeah, or no, not even few minutes. Oh, I'm back, but I guess I need. Oh, is this camera good, by the way? Well, camera, but it's mirrored. Yeah.
This has a setting mirror of the camera.
Oh, by the way, there is a seminar here. Mirror. What a nice default setting. Yep, we can continue. Wait, is it streaming? Yep, it's streaming. Okay, cool. So, um, I was giving some examples about the definition of FPT. Okay, so now
Exponential time hypothesis.
yeah, exponential time hypothesis, and the claim is that for every k, so k set with n variable instances is solvable in time 2 to the power cn. So exponential time hypothesis
is not so.
not solvable in 2 to the power n. So it's very common hypothesis, also like an approximation for vertex cover problems. So we had the two approximation last time. People try to improve, and for various constances, there are various computational complexity hypotheses. So it's really, I still need to learn all this. This kind of recent progress in the last 8 years. Okay. So let's now say what is kernel. I will do with an example, and as usual, I will use vertex cover problem. So idea of kernel is to reduce the size of the problem so that it becomes small, and then we can improve the time a little bit. So what did we have before for runtime on vertex cover? We had 2 to the power k poly n. And so we will improve 2 to the power k poly k plus poly n. And so the exponent only becomes proportional to polynomial k. So it's only a small improvement, but we will also expand this technique to decrease the exponent, not for vertex cover problem, but for many other problems. This is our plan. So to minimize exponent.
For FPT, f of k is exponential time. Yes.
Yeah. Here is exponent. So when we know that problem is an FPT, then our focus is on decreasing this function. So yes. Note that the clique problem is solvable in time n choose k, which is essentially n to the power k. So clique is not an FPT, and under exponential time hypothesis, it's not possible to solve it in time small o of k, if I remember correctly. So it's topic for next lecture. So we will prove this result.
And why polynomial of n is smaller than
Polynomial of k. So if the graph is huge, but you still want to find a vertex cover of size 100.
I mean, why it is smaller than len of x and plus k?
Sorry, this was what I was just telling before. So there are 3 levels of problems. So the clique problem is solvable in n to the power some function of the parameter, and that's called slice-wise polynomial. So if it's solvable in f of k, n to the power g of k. So this is called slice-wise polynomial. And we know k colorability is not slice-wise polynomial under exponential time hypothesis. Okay, what I'm saying might be wrong because we have polynomial. So we need a stronger type of reductions, and I need to be careful with the statement. But that's kind of the idea. We will have, even for k equal to 3, we won't have a polynomial. So sorry, yeah. 3 colorable. If P differs from, sorry, let me say it right. If P differs from NP, then K colorability with K as parameter is not slice-wise polynomial time solvable. And so the class of slice-wise polynomial time solvable, it's called XP. I will repeat it next lecture. We won't need it anymore in this lecture. But just for background information, that's the difference. So here we will have n with a constant times f of k. And what we will say now is, what we will prove now is that if we have this time, then we always have this time. It's one of the consequences of every FPT problem has kernel. It will, okay, but let us speak about specific example first. And so how it works. So let us think about branching problem with each time. We will have various reduction rules. So imagine that we have a graph and we want to know whether it has so input graph. So the parameter is k graph. So we always assume parameter as part of the input unless we say differently. And the question, vertex cover of size. Okay, so now I've said that. Imagine that we have a node of degree k plus 1. Then I claim that we can reduce the problem because we know this node must be in the vertex cover. If it's not in the vertex cover, all the neighbors must be in the vertex cover. But this is impossible because we need k plus 1 nodes or more. And so if degree is more than of node is more than k plus 1, what we do is we add this node to the vertex cover. And so we can remove this node and all of its neighbors. No, we can remove the node and all of the edges. And then solve the vertex cover for k minus 1. Because we can at most k. And so we can iterate this. And so this is the first reduction rule. And so we can have more reduction rules. For example, if we have isolated node, what can we do?
Just remove the node.
Yeah, we remove the node. So here are reduction rules. If degree is more than k plus 1, remove, if degree of v, remove v, and k goes to k minus 1. Remove isolated nodes.
Also, if there is a leaf, then we can remove the another node, which is one endpoint of the edge is a leaf, and another node we can add it into the vertex cover and remove.
Yeah, exactly. So, but I will not repeat it. It's homework task. Very good. No. I mean, it's the hint for the homework, but you still need to calculate something. So it's not all of the homework task. Okay. And then if we have applied all the rules until it's no longer possible, then there is a third rule. If the graph has more than k times k plus 1 nodes, then we say no vertex cover. Then answer no. Negative answer, no vertex cover of size at most k. Okay, so now we understand why these rules are correct. It's obvious. Now, why is this rule correct? And so we claim that if the graph is big and we can no longer apply these rules, and so we don't have isolated nodes, and we all nodes have degree at most k, then we know that, so if this t thinks is true, and the graph is strictly more, and the graph is strictly more than this, then we can directly say no vertex cover. So why is it happening?
Because every edge has a degree of at most k, so the maximum number of edges that can be covered using
Yeah.
k nodes is k times
Yeah.
one.
So let's look to vertex cover. So exactly like you say.
Okay.
So here we have k nodes in the vertex cover. And so we know that so what is the maximal number of nodes we can have in the graph at this point? So we know no isolated node. So every node in the graph must have some edge, at least one edge. We also know that if a node is not in the vertex cover, then its edge must go to a node in the vertex cover. So assume that this is our vertex cover. Every edge must go to have one endpoint in these nodes. So what's the maximal number of nodes we can have? And so all the edges are on these nodes. And in the worst case, the edges go to different nodes and a different set of nodes. So maximal number of nodes, well, this can be adjacent to at most k nodes, here also at most k and so on. So in this level, we have at most k squared nodes, and here we also have k nodes, so the vertex cover itself. So we know that if vertex cover exists, its size must be at most k squared plus k. And so this is third reduction rule. And so what we have done, after we applied reduction rule and we then produce the answer, then we obtain the graph of size k squared plus k. And this is ideal kernel. So a kernel is polynomial time algorithm that reduces the input to a smaller input of size, some function of k. So we go from a graph whose input is size n can be arbitrary, and k is also the input. And after polynomial time procedure in n, we end up with a problem whose size only depends on k. And now we can brute force search on the reduced size. And so this is a new proof that we have I lied to you. I said 2 to the power k poly n, but for this we need a more advanced idea of a more powerful kernel. And so we don't have this thing. So what we obtained here is we have the runtime is some function f of k, which is basically 2 to the power k squared plus k for brute force search. No, sorry, it's right. And now we can run the previous branching algorithm. Sorry, what I said is correct. So what we have here is 2 to the power k poly k. And because we reduce the graph to size k squared, plus the running time of our reduction algorithm. And so first we reduce graph poly n time, then we need to find vertex cover of size k, but now among k squared, basically k squared node. Okay, so this is idea. And so what is general definition of kernel? So kernel is polynomial time algorithm that satisfies two additional conditions. First, it should produce equivalence instance. And second, the size of the produced instance can only be a function of k. So it's bounded by a function of k. Well, k. So k is a mapping from a parameterized problem. This kernel, if three conditions hold, one, k runs, well, let's give argument, k x k runs in time. Oh, and I should say it oppositely because I said h k x runs in time, length of x plus k, So I always, the size of the object is length of word plus k in unary. So be careful when we use parameter. Parameter is given in unary. Length of k to the power. So yeah, time. Polynomial and length of k. Second, you remember what was second?
The answer for the kernel and
Yeah.
the initial
So yeah,
problem.
Size of k
okay, size.
is bounded by g of k, where g is computable function. And third, equivalence. Kx, kx. In the problem P, this kernel for problem P. Only if ax and p.
Why is it important that bound functions are computable?
Yeah, there are some pathologies. We don't want and otherwise we can have undecidable problems that are fixed parameter tractable. So you can think about very large inputs, but that solves the halting problem. So so you have a program followed by any number of zeros. Okay, you can do there's some weird, actually, I don't know concrete place where I say, oh, here it's important. And some authors, they drop these conditions. But I'm a bit worried to drop it because I can understand that you can have very weird things happening if you compare very large inputs to small parameters. Okay, yeah. So I'm worried that there will be at some point some special case where suddenly it's needed. Okay. Yes. And now here is our main theorem. Or should we do another example?
That makes sense.
Yeah, let's do our main theorem. So problem is FPT if and only if it has a kernel. So one direction is easy. So you should think about which direction it's easy.
If it has a kernel, then it's
yeah, indeed, that's the easy direction. And then it has kernels. Okay, and so easy direction, if it has kernel, it is FPT. So why? Well, we first reduce the problem, and then
it's not able to do it.
wait a moment. So we oh wait. I need a bit more. Problem is, sorry, I should say decidable problem. Yeah. Decidable problem, it means that there exists algorithm that decides whether whether pair is in the input, yes or no. So
Okay, now
it works.
Now it works because we just f of k is like maximum time to solve the problem for each input of size k.
Yeah.
Well, it's kind of because it's just
No.
like I mean the bound is kind of trivial.
Yeah. So for decidable problem, the following is equivalent. Let me write it correctly. So
There are
P is decidable. Then following.
But FPT doesn't contain any undecidable problems because there is for each problem.
Yeah, but in
there is
one of the so if it has kernel, we don't have a guarantee it's decided. Yeah. So here we have one P has kernel, and two P is FPT. Okay. Yes. So now it works. So if it's FPT, then we reduce problem. So we will have a problem of size at most G of K after the reduction. Then we say it's decidable. So we run an algorithm that runs in computably bounded time. And the worst case runtime, we can compute the upper bound. And so then we run this procedure to decide our problem. And so the runtime will be of this procedure will be polynomial, so poly. And so to decide the pair kx, we will have time poly length of x plus k plus so the time to reduce problem plus so if this is decidable in time h of length of x plus k. And so this is decidable if this is the run bound. So then the runtime is also bounded by decidable function. And then here we have the bound g of, so the runtime will be bounded by h of g of k. And because we run the decision procedure on outputs of the kernel, and the kernel is bounded by g of k. So if we have a monotone function on the instance size, then so here I assume h is non-decreasing. Then this is correct bound. Okay, yeah, up to some polynomials for my handling. Okay, so we just proved that the upward direction is okay. Now we need to prove downward direction.
Oh wait, what was it? Can you
sorry.
repeat what was the generalization then?
I'm wrong. So we just prove the other direction. We prove downward direction is okay. And now we want to prove upward direction and find the kernel. Yeah. And this is kind of so simple that's a bit remarkable. So what is algorithm for kernel? So here we have some C, and we have a decision procedure. We will run it 4 times size to the power C plus 1 and check whether our algorithm runs. So run decision procedure. So there are 2 cases. Either our decision procedure terminated, and then we know the answer. So then we output a small fixed instances, yes or no, according to the answer. And if it didn't halt, then we output the instance itself. That's the algorithm. And then we will check the 3 conditions of kernel. Okay, so let me write it. Run decision procedure for time length of x plus k to the power c plus 1. So here I use that parameter as part of the input so that I know it. So and then 2 cases. If how answer. That means that equivalent is of fixed size, and otherwise output the pair kx. So that is the kernel procedure. So algorithm okay.
We need to prove that size of x is bounded by some function k.
Yeah. So here we need to prove that
That's the only
the size of a of x, sorry, kx is bounded by some g of x, g of k.
Conditions 1 and 3 are.
Yeah. So condition 1, it runs in time polynomial in size of input. This is by the construction. Number 3, equivalence is also okay, because in first case, we know the answer and we output equivalently. In second case, also. And indeed, why is the size smaller than some function of k of x? Well, it is okay, so we understand that the runtime is big. Runtime is here. And we know that the runtime is more than this thing here. Now compare it. We know that this is bigger than this.
So f of k is greater than length of x plus ka. So the f of k is the desired.
Yeah, so I need some space somewhere. Okay, you know already what this here. So what do we have? Length of x plus k, c plus 1 is bigger than length of x plus k to the power c times f of k.
Less than, not greater than.
Yeah. So this we have. And now we can cancel this factor and this c here. So what they're saying is that our instance is already small.
And why we know that it is smaller than.
Because there is an algorithm that answers correctly in time f of k times.
Yeah, by FPT. So our problem is FPT. Here is the definition. So it's ridiculously easy proof. Yeah.
But it is f of k, which can be exponential.
It doesn't matter.
Yeah.
The only thing that matters is that.
So that's what we have to prove. That the size of reduced instance, which is the size of the instance itself. And so here we need to prove that x plus k is smaller than g of k. That's what we need to prove, where g is some computable function.
But f of k can be exponential. In the definition.
Yeah. So we have that f is computable.
Yeah.
And we need that g is computable. Here in the definition, g needs to be computable. And so what we do is we set f equal to g and it works.
Still, if we remove the condition that f and g is computable, that nothing breaks.
Ah, good point. Yeah. Yeah. But I said there is no place where I. So if we both drop this computable, if both here and here, nothing breaks. It's correct. Okay, so now we prove the theorem. So we have explained what is kernel, and we proved the theorem that it's equivalent. This thing we also did. And so now I still need to explain why. Okay, are there more questions about this theorem?
Yes. So why it is less than.
Yeah.
It is clear then that we can do f instead of g, but it isn't clear for me why.
Yeah. Why we got later this thing? Yeah.
Yes, why okay. It is less than.
So we have to prove number 2 here. We need to guarantee that the output is always bounded by f of k. So, well, there are 2 cases. Either we output the answer, but then it's bounded by a constant, or we output k of x, k and x. And so,
we run the algorithm for length of x plus k time in power to the c plus 1 time.
Yeah.
So it means that the algorithm from the definition of FPT runs longer than this thing. So the bound for
it's
like the algorithm is greater than.
You should have strict inequality.
Yes.
Sorry. I started to explain everything and then Okay, cool. So now we are almost done for this lecture. So I wonder what I'm forgetting to explain. I lost, I prepared on the paper what I should explain and then lost it as usual. Okay, so then let's, vertex cover in this time. Okay, so let's think about the branching algorithm that we had. It's very short, actually, the algorithm. So what was our strategy? Pick the nodes of largest degree. Our plan is to make sure that we observe that we can always take a node of degree at least 3. Because if no such node of degree at least 3, so let us add a reduction rule to the kernel. If all the nodes have degree at most 2, then we can give the answer directly. What does it mean that all nodes have degree at most 2?
The graph is the union of cycles and
paths. And what is the smallest vertex cover of a cycle?
Take half of nodes.
Yeah, if the cycle had even many nodes, then we take each of the half. And if it's odd many nodes, then half
plus
rounded up.
Yeah.
And for paths, similar. We also take half. If the length is odd, it's like a half rounded down. And if the length is even, it's exactly half. Okay, so now we know that we branch. And so either we, in the recursion, we decrease k by 1, and in the other reduction, we decrease k by 2. And so now we will give better bound on the size of the tree, because it's like very unbalanced tree, but recursively it's unbalanced. And it gives us exponential improvement of the size of the tree. And the runtime is size of 3 times polynomial, well, polynomial in k. Well, definitely. What we have here, our tree, g and k, and then we have a branch, gk minus 1, gk minus.
Wait, 1 minus 2 minus 3.
Sorry, minus 3, yeah. Good point. And so on. So let us have some function s that about the size of the tree for any value of k. And we know s of k is smaller than s of k minus 1 plus s of k
minus 3 plus 1.
Minus 3 plus 1, indeed. And so now let us make another variable. Let us say that t of k is equal to s of k plus 1 to get rid of the plus 1.
Mm-hmm.
And so then here we have t of k minus 1 smaller than t of k minus 1 plus t of k minus 3 minus 2 minus 1 from here minus 1 plus 1, and now we can drop all this nonsense. Yeah, so we just shift our bound.
Yes, and now there is an explicit recurrence
Yeah.
formula.
And now we will guess that t of k is equal to alpha to the power k. And then let's check which alpha works.
Mm-hmm.
So here we have alpha to the power k smaller than alpha to the power k minus 1 plus alpha k to the power minus 3. So let us divide by alpha k to the power 3. And so we have alpha to the power 3 smaller than alpha squared plus 1. And so we can solve, we can pretend this is equality to be tied. And then we solve for alpha and we find alpha 1 point. Good that I wrote the paper, so I remember the number 656. So we find alpha to be this thing. So we know that t is alpha to the power k. And so we know that s is 1 less.
Mm-hmm.
And then we multiply by, no, this is weird.
Where is n to the old 1?
No, that's the size of the tree. So in every node, we still need to do some work, which is polynomial in k.
Mm-hmm.
And so now we have this runtime. And we have a little bit better because we have k to the power of 1 plus poly n, as we also apply kernel technique. And so if you do it a bit careful, then you basically have linear on the RAM machine. So they just multiply by k. And so there are some Chinese people, and they did much better. And it's something like 1.27 something. Let's say 1.28 to the power k times. So they have this in the exponent. And so what does it mean? How big can our graph be? Well, so with this, you can have this is basically square root 2, a little bit more, 414, and this is 47. So so with brute force, you can go up to 80 in seconds, maybe 120 if you wait a long time. So with this algorithm, you get twice more, so close to 200. And with the Chinese algorithm, well, they're probably huge linear constant, but if we ignore them, then it's like up to 400. It's really a very long construction, and then afterwards people start to use computer algorithm. So there's just so they recurse to k minus 7 or something and k minus 3 by enormous case analysis. Like, so they make many cut rules, and then they analyze like so that they force the degree of the graph to be 7. But they do it in a clever way that they also save here. But okay, you need to have huge patience to to work it out. But the result is that, yeah. Okay, so if your graph, if k is at most 200, it means that so in theory you are safe, and practice you're definitely safe if you do a few advanced things.
So exponential time hypothesis somehow related to like the base of the like this number is bounded by 1 plus.
What you say is correct, but this is not what we're saying. So exponential
that's
time.
what you're saying, but it's like considered to be probably true.
Yeah. So so there is a question. So our algorithms, they are of the form alpha to the power k, and there are people who say for planar graphs. I think, well, I don't know, for vertex score, for many problems, there is algorithm that run in the time alpha to the power square root k.
For planar graphs.
Yeah, for planar graphs. So the question is, can you do it also for non-planar graphs? And this would violate exponential time hypothesis for many problems. And so next, I still need to read a little bit and decide for next lecture, but we will prove lower bounds, because it's like nice for theoretical computer science people. Okay, so that's it for today. There was one problem we didn't do. So you can have problems where you have two parameters, and then to define parameterized complexity by two parameters, you just take the sum and of the parameters, and you can apply this definition, or you can say it must be bounded by a computable function of the two parameters, and so on. This is equivalent. And so the example is independent set where both the size is and the degree is bounded. So we spoke about clique problem when the degree is bounded, but similar happens for independent set. But you can think about it for exercise. It's not so difficult. The idea is that if the graph is big, the answer is always no. Okay, so that's all. So despite technical trouble, we're only a little bit over time. Okay, see you.
Or maybe you just forgot to tell us how.
Yeah. No, I think we got everything. Yeah, I will write notes. It's my plan, but it's difficult. I have